Have you selected your topics? You?
did something, yeah, it's called the same thing that you suggested.
High pressure.
Yeah, piezophilic.
Perfect.
Yeah, I want to talk about the physicist's view on human consciousness.
Oh.
Great. I look forward to that. We might go on for more than 10 minutes, but anyway, that's interesting.
I am sort of thinking about photosynthesis.
Okay?
Not yet.
Not yet. Great.
Not yet.
Not yet?
Not yet, but I think I'm going to present that bit.
The one of not yet. Okay? No.
Not yet.
Biomembranes. Okay. Good. Okay, so I have quite a bit I want to cover today as well. Let's see how much we get through. So we ended here. We had a discussion about hydrophobicity, and we said one of the measures of hydrophobicity in a liquid is to study its density fluctuations. So the probability to create cavities. Okay? The likelihood to create cavities. And for spherical cavities, the theory goes that at small radii, the work required to create the cavity grows with the volume, which is why this is linear, because this is the work divided by the surface area. And then after some length, after 1 nanometer, it becomes, grows as the surface area. And this ratio is the surface tension, essentially. So there's a 2-length scale behavior for hydrophobicity for a spherical object. Okay? Okay. Now, just to before we go into understanding this theory a bit, I just want to give you some more phenomenological ideas. So, one of the questions that in biology is why do proteins, why do solutes want to aggregate? What's the driving force for them to stick with each other? It's the same question of protein folding. What causes the protein to stick with each other? And the argument that was suggested decades ago by Kauzmann was, if I have a solute like neon in water, then neon doesn't like water. So these interactions are not favorable. There's only dispersion, van der Waals interaction. So what Kauzmann suggested was that water forms ice-like cages. Okay, so this is like a picture representation of an ice cage. And so he believed that, and this was an idea that caught on quite a bit in the community, was that if around a hydrophobic solute, and also in water around proteins, would be significantly perturbed structurally and dynamically. So it would be more ice-like, it'd be slower. Okay? So this was known as the Iceberg Model. Why was this model invoked? Well, the idea is that if I have two solutes, two neon solutes in water, and I bring them close to each other, and they both have an iceberg cage around them, then when they come next to each other, this sort of liberates or gets rid of water, and this increases the entropy of water. So the driving force to put these two solids together is suggested to be an entropic one, because when you bring them close, this reduces the effective surface area that these two solids are exposed to the liquid, and this enhances the entropy of the surrounding solvent. Okay? Okay. So that, yeah, please.
Aggregation, does an aggregation occur even at, like at room temperature, maybe temperature? Then,
yeah.
If you talk of water forming an iceberg thing, I understand that the icebergs are associated with very low temperatures.
Hot temperatures?
Very low
temperatures.
temperatures.
Sure,
So
I agree. Yeah,
Why does it come? Why is it valid to leave it as it is?
I completely agree. It's not valid. It's not valid. So, and there are various ways one can prove this. Okay? So, I'm just giving you kind of a bit of history on some of the ideas that have existed. So, you're right. These ideas were debunked, and they were debunked by experiments. So, this is krypton in water and krypton in a clathrate. So, you know, when you go deep into the ocean, under high pressure, you form something known as methane clathrates. So these are methane molecules surrounded by a cage of water molecules. Okay? And so these are experiments that look at the structure factor or the pair correlation function of krypton in water and krypton in a clathrate. Okay? Krypton in a clathrate is really more like an iceberg. Okay? And you see, krypton in the clathrate has much more structure. Okay, it looks more ice-like. And then they do the same experiment of krypton in water, so at ambient temperatures, and you see that there's a big difference between this structure factor and this structure factor. So the notion that at room temperatures, a hydrophobic solute creates an iceberg was debunked. It doesn't make sense. And this experiment and numerous other experiments were able to show that this was in fact not true. Okay, because if it was true, this thing would be much closer to this. Okay, you would expect much more structure in the pair correlation function because it's more ice-like. Okay, so I'll skip this and now get into sort of building on the discussion that we were having in the last class, and also this two-length scale behavior of hydrophobicity. So if I want to put a solute in water, and I want to ask what is the solvation free energy to put that solute in water, remember for a hydrophobic solute we said that the change in free energy would be positive. For a hydrophilic one it would be negative. And so the way to think about this is the following. So I have a liquid. Before I put a solute in the liquid, I need to create some empty space. So I need to open up a cavity. Once I create the cavity, I can put the solute inside. I put the solute inside, and then I turn on van der Waals interactions. And if it's charged, I then turn on electrostatic interactions. Okay? This is, of course, not what happens in reality. This is not how you dissolve a solid there, but this is, it's analogous to something like a thermodynamic cycle that allows you to understand what the various contributions are of van der Waals to the free energy, and then to electrostatics to the free energy. Okay? And so, more formally, e to the minus beta of the free energy of putting in a solute, so S is some general coordinate that defines the solute in a liquid, is basically a Boltzmann average that includes e to the minus beta, the energy associated with creating excluded volume, turning on van der Waals interactions, and then turning on electrostatics. If I have a hydrophobic solute, this thing is 0. Okay, and this should not be a surprise. This is just coming from the partition function. So Q equals e to the minus beta free energy. And I'm taking that e to the minus beta free energy and writing a Boltzmann average in terms of the partition function. The R here is just a subscript that tells you that you have to average over solvent configurations. Okay? Okay, so the total free energy is a sum of the free energy associated with creating some excluded volume. That's what we discussed the other day. So remember we said there was that Pn equals 0 term, okay, the probability of having 0 particles, that's this part. And then when I put a solute inside, there's a free energy associated with the turning on van der Waals interactions. And then if it's charged, I have a free energy term associated with the electrostatics. Okay, so this is the typical way that one thinks about the thermodynamics of solvation, of putting in solutes in water. And so this is the type of thing that one can, numerically evaluate. You can numerically evaluate all these different components. Okay, so let's focus on the excluded volume part, because this is the hydrophobic part. So the hydrophobic part we discussed was, I want to sit myself in a liquid, I draw a sphere around me, and I ask, how many particles are there in this sphere? And by counting the statistics of the number of particles in the sphere, I get these types of distributions. And so, for example, these are the probability on a log scale, semi-log scale of number of particles within a specific radius as I increase the radius. Okay, and this value here is what tells me what the free energy to create a cavity is. And there are two things I want you to take away from this. One is that the statistics of these fluctuations have been shown to be Gaussian-like. Okay, so the statistics of the number density fluctuations are Gaussian-like. And two, this goes back to our discussion of the similarity between the radial distribution function of a complex liquid like water and a simple thing like hard spheres. So you can do the same exercise with hard spheres and you get very similar results. Okay, so cavitation at the short length scale has less to do with the details of the electrostatic interactions or van der Waals interactions. It has to do more with a geometrical packing. Okay, because of course the details of the free energy, the amount of work you need to do will change, but qualitatively, you see, you can learn a lot from the simple liquids about this term just by looking at hard spheres. Okay. Okay. So if the statistics are Gaussian of the number density, so then the probability of finding n particles can be written in this form. The average n here is basically related to the density. So the mean density, the density of my liquid times the molar volume. And the sigma v here is related to the fluctuations in the number density. This guy here, of course, is related to the compressibility. Okay, so sigma v, or the ease with which you create cavities in a liquid, is related to the compressibility of the liquid. Okay? Okay, so now this delta mu is just the delta G that I was discussing before, is minus kBt log of P of 0. And if this is a Gaussian, then you have an expression of how the free energy relates to the density, the compressibility, and here is the compressibility. Typically, this term, so if you look at how this term grows versus this term, grows much more slowly. So basically, the free energy associated with cavitation is dominated by this first term here only. Okay, so we can ignore this guy here. And so by looking at this, I can try to understand what is it that will make hydrophobicity less or small, or less or big. Okay? Okay, so now what things may I want to understand understand about hydrophobicity in terms of what I just showed you? Well, I told you about this puzzle, or this observation, which is that regardless of the solute, the hydrophobic solute, there's a temperature at which the the work required to create the cavity is, the maximum position is similar. What this translates to is that basically something known as entropy convergence. So there's a temperature at which the change in the entropy associated with solvating different solids is basically very similar. It's the same. Okay? Now, let's go back here. So I want to use this to try and explain why there's this entropy convergence. Okay? So I know that for small cavities, the work required to create the cavity is related to the density squared and the compressibility. So if I know something about the compressibility dependence as a function of temperature, if I know something about how the density depends as a function of temperature, then I might be able to understand why there's this temperature dependence to the hydrophobic effect. Okay? Now, what's very interesting about this, you see, look, the thermodynamics of hydrophobic solvation is related to a property of the liquid itself. Right? This is the density, it's the property of the liquid. This is the compressible, it's proportional to the compressibility. So these are properties of the liquid itself, and not of the solute. So in this formula, there was nothing about the van der Waals interactions of krypton or neon with the liquid around it. So this is saying something. It's saying that, you know, perhaps these features that one sees in hydrophobicity come from some special features in the liquid itself. Okay? And we know, at least on Earth, hydrophobicity is something that only happens in water. So, but then we go back to the question that we asked a couple of lectures ago, which is, what is special about water? What's special about water in terms of its density dependence as a function of temperature, and also its compressibility as a function of temperature? Okay? Okay. So I'll sketch out what the argument is. So we ignore this term. If I want to lower or increase the free energy, well, I have to reduce this term here or increase this term here. Okay? And so you can take this guy here. We're going to focus, so you can ignore this for now. We're going to focus on this part here. So I have a KBT, so a temperature dependence. I'm going to write the density as a function of temperature, okay, because the density does depend on temperature. And I'm also going to put in another function x, which depends on the compressibility. And now I'm going to ask, if I consider different liquids, is there a big change in the temperature dependence of the compressibility? Is there a big change in the density dependence of the temperature? And it's a very simple argument. If you look at, so this is from experiments. This is the compressibility of a liquid, water, and various other liquids. So you see something rather interesting, which is that the temperature dependence of the compressibility of water is essentially flat. It doesn't change much compared to other liquids. So intuitively, one would say, as I increase temperature, the compressibility must increase, right? water is weird. Water is weird in that it has this anomaly, which is that it has a minimum in the compressibility at 320 Kelvin. But in the temperature range that is relevant to biological problems, for the most part, this is just constant. Okay? So, what does this mean? This means that all this entropy convergence of hydrophobicity is all manifested in this term here. T rho squared as a function of temperature. So it has to do with the weird way in which the temperature dependence of the density, how the density of water changes as a function of temperature. Okay? And so you can do this exercise where you look at how these terms change, okay? Assuming this is a constant for solutes of different sizes, and what you find is that qualitatively you can essentially get this entropy convergence of hydrophobic solvation by just knowing how the density squared of liquid water changes as a function of temperature, which is interesting. So it's telling you that there's something intrinsic to the thermodynamics of water that controls this phenomenon. Okay? Okay, but of course, this is not entirely the whole story. For example, these terms here will also play a role, but for the most part, it's just a shift in the slopes, okay, by some constant factor. Okay. Are there questions about this before I move on? Okay, so you should at the very least have some sense of thermodynamic measures of hydrophobicity. Okay, how would one show that something is hydrophobic or not? Okay, so that's at small scale, small radii, small volume. But what happens when I go to large volume? Okay, so we've been in this regime, but now we want to go to that regime. And so there have been, of course, again, various ideas on what happens when you go to larger length scales. One of the ideas is that if I have two hydrophobic objects and I bring them together, so these are toy models, and these toy models have been used to try and understand hydrophobicity in proteins, for example. When you bring two plates close to each other, when you get to some particular length, then there's a vapor tunnel that develops. And so there are density fluctuations inside here, and when you get to some critical length, the density fluctuations get much larger, and then you form up essentially a big cavity, and then this causes the two objects to collapse. Okay, so in some ways you're creating a vacuum-like condition here, or vapor phase more correctly, and if there's a drying transition, so I go from liquid to vapor phase, that's going to drive the two plates to come close to each other. Okay, so that's one of the ideas. Another one that's related to wettability. So, how does a liquid wet a solute? Okay, so let's consider a spherical solute. Let's change its size, so that's capital R, and let's look at the density correlations of a water from that solute. So okay, when the solute is small, and you measure basically this is the pair correlation function. There's at the 0 point here, so this is up to the extruded volume, you see that there's a high density for water to wet the hydrophobic solid because there's this peak here. And then, okay, there are correlations that decay away, eventually going to 1. Now, let's make the radius bigger. As you make the radius bigger, what do you begin to see? Now you have bulk density, and then it's de-wetted. Okay, so there's low density here. So as you go from small to large in a hydrophobic solute, there's a change in, let's say, the physics of what drives the wetting process. Okay? And again, this is related to the fact that if we go back to, well, I have it here. In this regime, things are dominated by volume. Okay? That's why it's linear. Over here, it's dominated by surface area. Here, it's driven by entropy. There, it's driven by enthalpy. Okay, so there's this transition from entropic driving forces to enthalpic driving forces in the hydrophobic effect. Okay, so, well, you might be saying now, how the hell is this relevant to biology? So I haven't said anything about biological systems. So let me try and show you why it is relevant to biology. So these are, melatonin is a protein. I believe it's found in bees, in the venom of bees, or something like that, or snakes, one of the two. And it's a protein that's made up of, what are these things called? What's this? It's alpha helix. Okay, it's made up of several alpha helices. Okay, and what happens over time is that these helices, they fluctuate. Okay, they breathe, and as they breathe, there's a pocket inside here made up of water molecules. The helix is made up of hydrophobic groups, and the question is, what drives the breathing? What causes the helix bundle to collapse or to expand? How is this coupled to a de-wetting or a drying transition? Okay, so it's essentially, it's quite analogous to this problem. Okay? Of course, now you have a biological system that you're studying. Okay. And so let's look at this one here. Yes. So this plot essentially looks at how the number of water molecules in the cavity, in the center, change as a function of the distance between two of these helix bundles. And it's not surprising, okay? You see that there's this sort of correlation between the two guys coming in and the number of waters dropping. Okay, but you could ask, well, what's the cause and what is the effect? Who's the chicken? It's kind of the chicken and the egg problem. Okay, so this is something that people still argue about, but the argument still remains, which is that there are some collective density fluctuations that we've talked about in the context of hydrophobicity that are important for facilitating these types of drying transitions in biological systems. And here they then use some toy models and with, so they take flat plates and make them corrugated and rough and try to study how the drying transition happens here. But more or less it's the same story. Okay, so fine. But now now that I've told you a bunch of things about measures of hydrophobicity in terms of density, in terms of density fluctuations, what order parameters can I construct or look at to distinguish between something hydrophobic and hydrophilic? So let's say I put a water droplet on a piece of plastic versus a water droplet on, well, actually, how many you've all seen water droplets on leaves, right? Have you noticed something about them? What do they do?
Like something.
It's like it's not absorbed by the leaf.
Okay, it sort of it curls on itself. It forms a. Okay. Is there a way to quantify that? The contact angle. Okay, so contact angle is related to this Young's equation. Okay, which is related to the various three components of the interfacial energy between solid vapor, liquid solid, and vapor solid or vapor liquid. Okay, so if I put a droplet on a hydrophobic solute, I can measure the wettability by the angle that the droplet makes with the surface. If something is very hydrophilic, it'll flatten out, and I can measure some angle that tells me that it's flattened out. If I make something hydrophobic, then that angle will change. Okay? So the contact angle is a way to, at a macroscopic scale, to measure wettability. Fine, but that's, how do I relate contact angles to density and density fluctuations? I just told you that at the molecular scale, at the short length scale, what I need to think about are density and density fluctuations, the compressibility. So how do we go from here to what can I measure at the molecular scale to see if something is hydrophobic or hydrophilic? Let's think, so if I took a hydrophobic plate and a non-hydrophobic plate, or hydrophilic plate, how do you think the density would change?
Okay, density, or maybe the one that you were showing last time, what is that, G, what is G?
The plate correlation.
Yeah, so if it's hydrophobic, so if we start measuring from the plate,
Yes.
or the solute,
Yeah.
from the center, then it will be, let's say, very less or zero to a certain point.
Okay,
Then
great.
it will rise and it will be constant, like that.
Okay, excellent. So what, if I understand what you're saying, is you will have something like this maybe.
Yes.
Here, and then here. Okay, this is what you'd expect. This is what you'd expect. But this is not what happens. Okay, so it turns out that if you look at both hydrophobic and hydrophilic objects, the density correlations as given by the pair correlation both look like this. That's weird. Well, first, do you think it's weird? You're falling asleep. What do you see this as a surprise? First of all, okay. First, do you see this point, or no? Okay. So, did you see this point? So, if I'm hydrophilic, that means the substance wants to be wetted, so I must have higher density. If the system's hydrophobic, it doesn't want to be wetted, so there must be a low probability of being close to it. So, wetted, non-wetted. So, if something is hydrophobic, you might think that, well, near it there's less probability. Okay, if something is hydrophilic, it should be like this, because it wants to be. But it turns out that both hydrophobic and hydrophilic objects look like this. So the density itself doesn't tell you about wettability at the molecular scale. So let me show you a practical example of this. So let's see. Let's take. So these are two different surfaces. Okay, one is made up of trifluorocarbon, and another one is made up of these groups. Okay, so this is a surface with lots of these things. So the experimentalist does the following. They measure the contact angle here, and they measure the contact angle here. Okay, and they find that, look, when I have CF3, it's hydrophobic from the contact angle, and OH is hydrophilic. Makes sense. Okay, OH is more electronegative, and so more hydrogen bonds. This is less electronegative. This is more hydrophobic, so it's more hydrophobic. Okay, so from the contact angle, this is hydrophobic, this is hydrophilic. Fine. Now, you go in and you measure this, the density. And intuitively, you would say that this guy, so if I was to make a sketch of this, I would think that it would look like this. So maybe OH might look like this, and CF3 like that. Do we agree with this? Or no? It's the same argument. So, no surprise. Yeah?
I just don't agree because, for example, if we are talking of a surface on which maybe a drop of something has been put, I don't expect the density of the particle the density of the drop to change. It's the same drop. Maybe if there is some kind of mix.
So hold on. So first, you need to understand what it is that you're looking at here. Okay, so what you're saying is once you've got to this limit. So once you get to a certain volume, then density is number of particles of a volume. So the density of the droplet is. So you're confusing that with. Now I look at a particular length scale, and I ask and I count. How does the density in that region compare with the bulk? This is this is at the heart of the pair correlation function. So I'm not going to get into this now, okay? But look, hydrophobic, hydrophilic. The hydrophobic one has even a much bigger peak in the density than the hydrophilic one. That's strange.
Okay, it has a much bigger peak.
Yeah.
So, for example, I think we are looking at a certain constraint direction.
Okay, fine.
So, if we have, let's say, a surface
Yeah.
of one
Yeah.
by one,
Yeah.
and if we put a certain volume of, I'm talking in very small
Yeah.
volume of a unit,
Sure.
it's about how that solvent
Yes.
distributes itself over the surface.
Yes.
So if we, just looking at that,
Yeah.
if we had started measuring the density from the left hand side, there would be nothing of the hydrophobic picture. For example, it's not distributing it evenly over the surface.
Okay. So the response to that is the following. So this, I've made the droplet so large, okay, that basically it's so large that the left side and the right side is much far away from the bulk. So there's really, you have to imagine this is really a droplet which is so large that you really have a bulk-like density, which is why it goes to 1 eventually. Okay, over some length scale. But so what this is telling you is that the density itself is a bad measure of wettability. Okay, this sort of contradicts what I said 3 slides ago. Okay, well, why am I contradicting myself? Oh, because I like to. No. Okay, there we were dealing with a simple toy model. We're dealing with a big hard sphere and a small hard sphere, which is a water. And we were just looking at a simple model. But here now, I'm putting in some chemical details. When I put in chemical details, the story gets much more complicated. So, what you should understand from here is the following. The comparison of this curve, these curves to this curve, should bother you, at least intuitively. Because if wettability is related to a stronger binding energies, as you might expect, okay, to negative solvation energy, so favorable solvation energy, you'd expect that near the hydrophilic source there's a more tendency to form stronger interactions. So there should be a bigger peak compared to the hydrophobic guy. But this is not the case. And so the density itself, which averages out fluctuations, does not tell you or give you a good measure of hydrophobicity. Okay, so what does then? Okay. Well, what does is fluctuations. So there's a difference between looking at the average density and the fluctuations in the densities. And the answer to a microscopic or molecular measure of hydrophobicity comes from the fluctuations. And this is what's quantified here. So these are exactly the same types of distributions that I showed you earlier on. Okay, so these are these Gaussian-like probability distributions of finding a cavity near the hydrophobic surface, so this guy versus this guy. Okay, so rather than just looking at the average density, you look at what is the work required to create cavities at the surface. This tells you about fluctuations, and of course it's telling you about compressibilities. So the change in the compressibility of the liquid near the two surfaces is a much better measure of hydrophobicity, and you see it clearly here. So the OH, okay, it's this point here, it's more hydrophilic, and the CH3 or the CF3 is up here. Okay? So by looking at the probability of finding 0 particles or the free energy required to create a cavity, you get a much better measure of whether the surface you're looking at is hydrophobic or hydrophilic. Okay, so you have to distinguish between average densities versus fluctuations. This is the important message. And okay, so this is sort of very interesting. Just to show you, physicists are often scared. They run away from chemistry. Okay, and but this is a really good example of how, it's very important not to, because it can qualitatively change even the physics. So look at this. So this is it's a toy model. It's a surface made up of mostly OH groups. Okay, and then somewhere in the middle, I put one CH3 group or CF3 group. So it's a local perturbation. Okay, so I say I have all hydrophilic. Let me add a small impurity that's hydrophobic somewhere. Okay, and then you do the inverse of that, which is you have all hydrophobic, but then you add a small impurity that's hydrophilic. And now you can ask the same question. How does the presence of one hydrophobic group in a bath or a sea of hydrophilic interactions, how does that change my compressibility? Versus if I have all hydrophobic and I introduce one OH group, how does that change my compressibility? And you see it nicely here. So this guy here is the top. Okay, so as I grow the number of the size of the hydrophobic patch in a sea of hydrophilic interactions, the effective compressibility doesn't change much. But if I do the opposite, which is if I grow a patch of hydrophilic interactions in a sea of hydrophobic ones, you get a big change as the size of the patch changes. So now, let's go back to all these lattice models that we've been discussing. We talked about lattice models of, I had one hydrophobic group, one polar group, and I just focused on hydrophobic interactions. We had lattice models of a ligand binding to a protein, where in all those models you neglect chemistry. Okay? This is just a simple example of how, if you neglect chemistry, you can really qualitatively change physics. Okay, so there are too many models out there in the biophysics world that rely on lattice models, and it's a good starting point. But if you really want to have quantitative understanding of things, one has to worry about chemistry. Right? This is a highly non-trivial result, something that at least I wouldn't be able to predict it. Okay? So, another thing this is telling you is that, hydrophobicity and hydrophilicity has to be thought about in its context. So, the environment in which a hydrophobic or a hydrophilic object lives in will change the physics of the problem. Okay? Okay. So Now you may be asking, well, again, what does this have to do with biology, maybe? So now I give you a practical example of where these concepts become important. So we talked a lot about protein folding. Folded protein, partially unfolded protein. Okay? Now I can ask the same question. How does the compressibility of water change around a folded protein versus an unfolded protein? And all this is telling you is that when I go from a folded to an unfolded protein, okay, there's a rather big change in the compressibility of the water around it. So the enhancement of the fluctuations of the density of water around the protein will play an important role in changing the stability, the thermodynamics associated with the protein. And now it should make sense to you. We talked about pressure. I can take the pressure knob, I can take the temperature knob and change the stability of the protein. Why? Well, now you see that there are all these factors that can sensitively change quantities like the compressibility and so forth, as a function of pressure and temperature, for example. Does? Which one? And enhanced density fluctuations makes it more unstable. It's not. It's not good for the system. What does that mean? Yes? No. Definitely no. Okay, but this is a very, what do you mean by it's not good for the system? Like,
whatever system the protein has found.
it depends on the function of what will I, yeah.
So you're saying that means that there will be some specific function that will require that the protein should be stable?
Yes. 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 So there are these class of proteins that we also discussed, these intrinsically disordered proteins that that function only when they're unfolded. Okay. Okay. Let's see. I think I'll skip this and get into something else. Okay. Are there questions on hydrophobicity? Because I think that's all I'm going to say now about that.
If you have, like I saw you do comparison for OH and
Yes.
CH3.
Yeah.
So if you have different elements,
Yeah.
does the compositions of general compound affect the?
Yes. Yes. A lot. And that's why I made the statement that, unfortunately, chemistry matters. Or fortunately, depends on your perspective. So yeah, in constructing models for biological systems, one has to worry about these details, unfortunately.
When you have complicated many compounds,
Yeah,
might be very difficult.
absolutely. So the moment you start having things like transition metal ions, things like this, it's horribly difficult. Okay, but unfortunately, or fortunately, transition metal ions are part of biology. So, and well, this is, what do you mean they're part of chemistry and not a part of biology?
No, you said they are part of biology.
Yeah, they're part of biological systems, like your protein myoglobin that allows you to breathe has iron,
Yeah.
which is a chemical element. But now we're getting into pedantics. So, okay, fine. So, I'm not going to go through the details of this, but just to tell you about it, because this is something that is important. And this is something known as Marcus theory. So Marcus theory is a theory that Rudy Marcus developed in the 50s for trying to explain charge transport in the condensed phase. And so he got the Nobel Prize for this theory. And the systems that he was thinking about were the following. So I have iron, Fe3 plus, Fe2 plus, and I have an electron transfer from this to this, and then this creates Fe3 plus and Fe2 plus. So how do I understand what controls the charge transport? So I guess you guys have already learned some of this in Landau-Zener. Have you done Landau-Zener? No. Two-state model, electron coupling between two-state model. No? No. Okay. Okay, but so I have two charges in a liquid, and I want to know what is can I have a theory that predicts for me the rate at which the charge hops? In this case, it's the electron. Okay, so what is the rate at which electron or charge transfer happens? Okay, and in a condensed phase, or in a phase where there are where the ions or the charges are surrounded by dipoles, you might imagine that the dipoles must do something. So the dipoles are fluctuating, okay, they're reorganizing, and those fluctuations must respond to the change in the charge. Makes sense. If I have an Fe2 plus and I have an electron transfer and I create Fe3 plus, the environment must respond to the presence of a 2 plus or a 3 plus charge. Okay. So this is what Rudy Marcus began to think about, was can you formulate a simple theory that explains or predicts how the charge hops? Before he came up with this theory, people like William Libby thought that the rate limiting step for electron transfer was the electron hopping itself. Okay, so you have to go back to some of our discussions right at the beginning of the lectures, which is about time scales. So we have a lot of different time scales. What are the time scales in this type of process that control the rate at which the charge will hop? He argued that this has to do with only electron, that the rate limiting step was the electron tunneling from one ion to another. So it's only related to the off-diagonal elements of the coupling. So H12 squared. So if I have two states, the off-diagonal elements squared. That's the only thing that controls the electron transfer rate. And what he also said was, when the electron hops, or the charge hops from one ion to the other, the ions, the nuclear degrees of freedom, remain frozen. They don't move. Okay, so those are two assumptions that he made. Now, these assumptions are wrong. Okay, and they're wrong for the following reason. So, these are just two cartoon pictures of a potential energy surface for Fe2 and Fe3 and Fe2. Okay, so I have this and I have this. There are two surfaces along some coordinate. So let's imagine that I have water molecules around Fe2 plus and Fe3 plus. This distance if you change the charge, must change. So let me put it this way. If you looked at the pair correlation function, again, the radial distribution function between this and this versus this, you'd expect there to be a difference. Right? If I have a Fe3 plus, it should be shorter compared to Fe2 plus. Okay, fine. So this was known. But Libby says for electron transfer to happen, the nuclei remain frozen. They don't fluctuate. So that's one assumption he makes. And these reactions were known experimentally to take place without the presence of light. So that happened in the dark. And so one of the consequences of these two assumptions is that it violates energy conservation. And it violates energy conservation for the following reason. So if it happens in the presence, in the dark, and I have two potential energy surfaces, the Fe3 and the Fe2, the only way that you can go from this surface to this surface is through a vertical transition. If you're not allowed to move along this coordinate. Libby says, I cannot move along this coordinate. So the only way to do it is excitation. You have to absorb a photon. But the reaction only takes place in the dark. So if this happens in the dark, where does this energy come from? So Rudy Marcus was the first person to realize this inconsistency. So he said there's something wrong with this concept. So what else could it be? Okay, so that's what Rudy Marcus had in mind. Of course, before Rudy, Arrhenius, who got the Nobel Prize in Chemistry, had already shown that the rate of a process is related to the exponential of the barrier. The temperature dependence of this allows you to infer the barrier and this pre-exponential factor. And then later on, Henry Eyring and also Wigner, so Eyring was a chemist, Wigner was a physicist, they also came up with a very similar expression, so this was empirical. And then Eyring and Wigner showed more formally, using something known as transition state theory, that the rate of a process is given by, is proportional to the exponential of the activation barrier. Okay? So these ideas, these two things already existed. Now, what Marcus did was to try and figure out what the activation barrier is associated with charge transfer. Okay, so I won't go into the details, it's also rather simple. What Marcus did was he assumed that if I have two potential energy surfaces, the reactants and the products are characterized by Gaussian fluctuations. So they have a harmonic potential. Okay? So you assume that things happen in two harmonic oscillators. And if you make that assumption, what he was able to show is that the rate of charge transfer is proportional to this object here, okay? And this activation barrier is a sum of delta G0, which is the free energy difference between the two states, okay? And lambda. Lambda is something known as the solvent reorganization. So the energy required to reorganize the solvent around the reactant or the product. So this expression was a very compact way of relating the rate of charge transfer to thermodynamic quantities, free energy difference and solvent reorganization. Okay? And what he predicted was the following. So here you go. These are two harmonic potentials. I start from here, in order for electron transport to happen, or charge transfer, I have to go to the transition state, and then there's electron tunneling. And then I go into my products. And what Rudy predicted was that there are basically 3 regimes of electron transfer. There's this regime which he called the normal region. So in the normal region, if the delta G, which is the driving force, if this increases, the electron transfer rate increases because the barrier drops. Okay, so if I take 2 parabolas here and I start them like this, and I start making the driving force more, the electron transfer rate will increase. And then it gets to a point where the barrier is 0, which is here. Okay? Now, if I continue to do that, I go into a regime known as the inverted regime. So now, the electron transfer rate, or the charge transfer rate, is the barrier to go from here to up here. And as you make the driving force larger, the electron transfer rate drops because the barrier gets larger. So this is known as the inverted regime. So, and this was considered anomalous. Why? Because from the point of view of thermodynamics, if you have a larger driving force, you expect the reaction to spontaneously happen. Okay? But spontaneity doesn't tell you about kinetics. Kinetics is about activation barriers. And the activation barriers can depend a lot on the details of how the 2 parabolas are aligned with each other. Okay? So, normal, barrierless, and then anomalous. So this is what he predicted in the 50s, and then it was only 20 years later that people showed experimentally that this is actually the case. Okay, then this is why he got the Nobel Prize for his contribution to this. But photosynthesis, for example, one of the starting points is, I have a photoexcitation and then charge transfer. Does Marcus theory hold for photosynthesis? I don't know. Okay, so this is usually the starting point to consider all charge transfer, electron transfer models. And it's very important in biology. There are numerous biological processes that involve electron or charge transfer. Okay, so, this was the experimental validation. So that's the rate. You see, as the driving force increases, the rate increases, and then it becomes maximum, and then when the driving force increases again, the rate drops. So, normal regime, this over here is this thing, maximum, this, and then this side here is that guy. Okay? Okay. So I think I'll skip this. And let's see. Since I only have one more class. Well, the next class is going to be the presentations. But so I just want to tell you a bit about more practical issues of models. Let's go here. Okay, so this is more related to now numerics. So there are lots of different ways to simulate biological systems in the liquid phase or in contact with water. And there are there's a hierarchy of different types of water models. We've sort of alluded to many of these, or some of these. There's epsilon type models, dielectric constant. This is what is used in Poisson-Boltzmann theory. It's what gives Debye-Huckel theory. It gives things like the Burum length. Okay, so that. And then there are a whole class of other empirical type potentials that these are the types of things we did in the numerical 2 tutorial. Okay, so classical, no quantum mechanics, nothing. And then there are even better quote unquote better models that based on density functional theory. And you guys now are experts in density functional theory, or you're going to be after today. And in density functional theory is exact. The theory is exact. Okay? But there's the elephant in the room, which is the
Exchange correlation.
Exchange correlation. Okay. And so people have come up and tried to know with all sorts of assumptions and recipes for the exchange correlation. And it's just a zoo of things. And so because of the assumptions made to the exchange correlation, DFT in practice is not exact. And for water, for many years, it was not understood why DFT didn't work as well as people thought it would. And then it was discovered that what was missing was dispersion, van der Waals. So if you knew what the exact form of the correlation part of the exchange correlation was, then you wouldn't have to worry about dispersion, because dispersion is a part of electron correlation. But because you make assumptions, this is not exact. So now it's well known that in order to simulate water correctly, you need these GGA functions, they're called generalized gradient approximation functions, plus van der Waals corrections, okay, to treat the structure. So if you want to get this right for water, if you just use standard functionals, it doesn't work. You need to, you have to correct for dispersion. Okay, and then there's also more recent efforts to do quantum Monte Carlo. So to really treat the electron correlation even more correctly, but this is very expensive. All these are classical treatment of nuclei, usually. So the next thing in the hierarchy is things known as path integral, DFT. So you treat the electrons quantum, and you also treat the nuclei quantum mechanically. And now you know that the thermal de Broglie wavelength of the proton is significant. And so for a liquid like water, you have to worry about not only the quantum side of the electrons, but also the quantum side of the nuclei. Okay, so this is just basically a laundry list of all the different types of potentials. Now, okay, this we more or less, we didn't really get into this in the numerical 2 class, but these are molecular mechanics type force fields where you have 3 particles, you have point charges, and you tune the charge and the epsilon and sigma to reproduce experimental quantities. Okay? I think I'll skip this, or let's see. Maybe I'll show this to you. So typically, in many models, we constrain the bond lengths of both the water and the protein. And we do this because this allows us to use larger integration time steps. Okay, so this is just a study that shows how the density and the dipole, and also the surface tension, changes as a function of making the bonds flexible. So we know that the OH vibrations are on the order of 3,000 wave numbers. The bending is on the order of 1,500 wave numbers. So in a rigid water, those modes are frozen. They're integrated out. We don't consider them. But in reality, those are modes that are high frequency modes that are real, and they should be there. And this just tells you that if you look at the dipole moment of water in a model where you keep, which is rigid, the dipole, as you go from, this is an interface, details are not important, you see that the dipole is constant. But this is not true. In reality, there's a gradient. So by making the bonds flexible, you can account for to some degree polarization. Okay. So in all these fixed point charge models, there's no polarization. Okay. Okay, let's see. Just to show you, maybe this. So these are different models. This is the truth experiments, and you see the melting temperature for different models. In the case of this model, it's 190 Kelvin. The experiment is 270. And then there are adjustments made to the model, and some of them get it reasonably, quite well. This TIP3P, this is another type of empirical model where the freezing temperature is 145 Kelvin. It's completely off. Okay, TIP3P is a typical model that people use in simulating biological systems. Okay, why do they use it? Well, because that's what the original 30 or 40 years ago, the parameters were developed for TIP3P to work at room temperature. But all I want you to take away from this is that when you start, let's say I was interested in looking at the pressure temperature phase diagram of a protein with a particular model. I would need to really be careful about knowing how the water model itself, how its temperature and pressure phase diagram looked. Okay, because if you push the model into a regime of temperature and pressure outside of which it was parametrized, it can be very problematic. And this is actually one of the reasons why there's now an explosion of people interested in machine learning and neural networks. Okay, because the idea is, I don't want to have a potential where I reparameterize all these things. I don't want to tune Q and bond length and sigma if I want to simulate something at this temperature and at this condition. I want something that is transferable. Okay, and so this is actually one of the main reasons why there's a lot of interest in using these ideas of neural networks to have neural network-based potentials for, let's say, biological systems. Okay, I think I'll stop here. So, are there questions? Either everything is super clear or super unclear. Well, we'll find out in the exam. No question? Okay, good. So, Tuesday, 10-minute talks. blackboard. Yours might be a very interesting talk.
Might take
It might take much more than 10. So we'll leave you to the end. The last you'll talk at the end.
Like, if we want to like present some specific graphs or poster.
Okay, then you can. Yeah. This is fun. This is fun. Yeah. I don't want you to spend time to make a presentation. That's the. No questions? No. Okay. Yes, please.
So please tell me, just give me some recent developments in the field.
The
Recent developments.
recent developments in the field. So I can tell you from the, let's say, the theory side. I would say two very, very important things, maybe three. One is that in the last 2 decades, what? In the last 2 decades, there have been experimental developments in single molecule spectroscopy, single molecule experiments. So typically in most biological experiments, you do ensemble measurements. So you measure an ensemble of on the order of Avogadro's constant. But now there are experiments that allow you to do single molecule. So, okay, why is this relevant for us? Because some of these experiments in biological systems claim that there's a breakdown in ergodicity. Okay, so this ergodic hypothesis, which is that the time average of a product equal to the ensemble average, apparently can break down. Now, in most types of simulations and theory work, you are typically doing single molecule experiments, okay, on the computer or on the theory. And so there's some very interesting conversations going on about whether this is first true or not, and how to understand this breakdown of ergodicity. Yes, that's one point. A related point is crowding. So most of our understanding of biology is built on, let's say, single particle view, a single protein doing its own function on its own. Now, with all the explosion of good experiments, data science, network analysis, people are finding that your problems with your gut, okay, is related to everything. So it can be related to mental problems, it can be related to your some probability of you getting Alzheimer's disease, So I think what's happening now is that there's because of all this wide spectrum of data and the ability to build good models based on all this data is giving a more collective picture of biology. So I'd say that's really cutting edge now and still not understood at all. And then the final thing is what I mentioned, which is I think the developing sophisticated models with this machine learning and data neural networks is where this is going to go. So being able to simulate a cell with all the electrons and all the nuclei in there. And maybe that's where quantum computing will help. Who knows? Maybe 100 years.
That's not far.
Well,
And then work hard.
yeah, it is far, but unless there's something revolutionary in the number of qubits and error correction and all this stuff, I think it's going to be a lot of time before we see quantum computing in real chemistry and biology. Okay, but I'd say those are the things that people are thinking about for the future.